Hello, my name is Alexander Lehmann and I would like to show you an easy tutorial on writing a Raytracer in Common Lisp. And the reason I'm doing this is because I would like to show you that Lisp is neither difficult nor sophisticated nor for quantum physicists or whatever, but instead actually it's very much fun to program in Lisp. And let me start out with giving you a short overview of what is going to come. At first we'll have to deal with some linear algebra because there's no Raytracer without linear algebra. So we have just to stick with it. Then we'll talk about basic ray tracing, reflections and refractions, and maybe, if time permits, meshes and acceleration structures as well as textures. And while on the left hand side you see the Raytracer related topics, on the right hand side you can see the Lisp related topics. So because we want to implement everything as object oriented as possible, we'll be using CLOS, the Common Lisp object system. Also we'll be using ASDF, which basically enables us to define inter-package dependencies for the packages that we are going to write, or external packages or whatever. And on the other hand also allows us to easily load or even install external packages, like the ones that you can see on the bottom right, like CLPPCRE or ZPNG. These are examples for working with regular expressions or PNG images, at least writing them. And last but not least, also the CFFI, that's the Common Foreign Function Interface. We will use that when it comes to textures, because this package enables us to call C library functions from within Lisp. And we'll be using the Simple Direct Media Layer, the SDL library, to load images for us. So because, as I said, ZPNG is just for writing images. Now, okay, as you can see, there's a lot of stuff on this page, so this tutorial will be split up into multiple parts. However, let's just begin with our first package, the linear algebra package. We'll be using Emacs and Slime. Of course, there are other IDEs out there, but Emacs is free and Slime is also free and very, very nice, has convenient functions. You'll see that as we get along. Okay, we'll start out. The first thing that we want to do is define our own package. We'll call that linalg, and we'll use another package called CL. That's a standard Common Lisp package that defines the standard functions and operators that we're going to need. Later on we'll also export symbols, the symbols that we are going to define that either stand for the functions that we define or variables, values, whatever. So next thing, we want to make sure that we are really in that package, so we call in package linalg. That's it so far. Let's start up Slime so that we can compile and see if we have made any errors. So I hit meter X and enter Slime, and that's it. It automatically starts. Go back to the buffer and hit Ctrl C, Ctrl K. And now we see at the very bottom of the screen that the compilation finished without any errors, warnings or notes. That's fine, but anyways, that's just what we expected. Good. Talking about linear algebra, there is no linear algebra without matrices, and so let's just define our own matrix class. We do that by using def class matrix. The empty list here implies that matrix has no superclass. We won't need any superclass anyways. However, in CLOS, objects have so-called slots. And one of those slots that we are going to need is the number of rows of the matrix. So let's just call it rows. And we'll also define an init argument for that called rows, so that when we instantiate a new instance of matrix, we can set the number of rows via the rows keyword. We'll also define a init form that is only automatically taken if the keyword rows is not specified. However, we want to the number of rows to be specified. So just in case someone forgets to specify rows, we throw an error saying rows must be specified. And we also want easier access. There are several ways to access the slots of an object. However, the dev class macro makes it very easy and convenient for us by just specifying the reader keyword together with a name that we want to use, something like matrix rows, for example. So later on, if we want to know about the number of rows of a matrix, we can just call the function matrix rows. We also need a slot for the columns, and for the number of columns that will basically be the same. I'll just copy that and exchange all rows with columns. Place string, rows, quotes. Okay, we're done with that. And last but not least, of course, we need a place where we can store the matrix data. The elements of the matrix, we call it data. The init argument data, no init form at this time, because later on we're going to write our own method, something, yeah, let's say like a constructor. CLOS doesn't care about constructors or destructors or anything like that, but instead uses the concept of generic methods. I don't want to go into detail here because this would take too much time, but I think you'll get the idea as we get along. Whereas the number of rows and number of columns are fixed for a matrix, we want to be able to access the data array, not only read it but also write it, and thus yeah, we could either specify a separate reader and writer, or we could just use the accessor keyword and specify a function that does both for us, and we call the function matrix data. Good. That's it so far. We've defined our first object. Compile again, no error, very nice. And as I said, oh yeah, maybe we should now go ahead and I said that every package exports a certain number of symbols, and of course we want to export our matrix symbol for the matrix class. So we write export and then matrix, and that's it. What now we do need is something like a constructor, even though I just said that CLOS doesn't have constructors. We'll instead use or write a method called initialize instance, and after the keyword after specifies that the generic method initialize instance that was implicitly declared by dev class will be called before our method is called. And yeah, okay, so we just need this method, and it's going to be specified for matrices. We have the variable m, which is a matrix, and in addition to the keywords that we have provided above, like rows, quotes, or data, we want to have another keyword, generator. You'll see later on that this keyword will allow us to use a so-called generator function that we can use to initialize the elements of a matrix. But first of all, we have to make sure that rows and calls are greater than 0. We'll use simple assertions for that. There, of course, are numerous other ways that we could do it, but assertions are nice at this point. So we assert that 0 is always smaller than matrix rows m. If not, we throw an error message, or yeah, we provide the string for the error message. Rows must be greater than 0. That's it for the rows. Again, copy that because we'll do the same check for the number of columns. Sorry. Place string rows quotes. Okay, done with that. And now the thing is, we want to have different possibilities to call to create instances of matrix. For example, we want to be able to create a matrix whose elements are initialized with 0 by just specifying the number of rows and the number of columns. We also want to be able to, at least from within this linear algebra package, instantiate matrices where the number of rows and columns are specified, as well as the data array. And last but not least, we want to make use of the generator function. So at first we have to check if, what was that? I'm sorry, if the data slot has been bound by the initialize instance method that was created by dev class. We check that just by asking for the slot bound predicate with slot bound p. And by the way, at the very bottom of the screen, you can see that Slime helps us here. If ever you forget a keyword or argument or whatever of a function, you can just look at the very bottom, and then you see, like here, that after slot bound p, the function's first argument is the object, and the second argument is the slot's name. Our object is of course m, and the slot's name is data. Not matrix data in this case, because the slot's name is data and matrix data is only the accessor function. Okay, so if this slot is bound, we have first of all to check that the dimension of the provided data array is the product equals the product of the number of rows and numbers of columns. So as there will be another assertion, we'll start with a block here, problem, and assert that the number of, or let's say the length of matrix data m equals the product of the matrix rows and the matrix columns. And if not, again, an error message. Data dimension should be okay, and we provide a little bit more information here. And matrix rows times matrix columns. And the second thing that we want to assert is we want to make sure that if data has been provided, no generator is provided at the same time, because this makes absolutely no sense. So we assert not generator, or otherwise say data and generator may not be specified at the same time. Okay, we're done with that. This was the true case. So if we had, if data was already bound, we checked the length of the array, and also that no generator has been specified. If data has not been specified, then we have the two cases that I talked about before. The first case being the one that no generator has, or no, let's just switch it. Let's make the first case, if a generator has been specified, we want to initialize the data, the elements of the matrix, with the results returned from the generator function. So at first we have to check, is there a generator function, if function p generator, and if there is, we, another block, we need to set the matrix data slot of the matrix, and we'll set it to a new array, make array, and the dimensions of the array will be of course the matrix rows times the matrix columns. The element type will be a single float. This is actually, specifying the element type is actually not necessary, but it helps the Lisp compiler to create faster code. And okay, secondly, we want to iterate over the matrix. I will specify our the actual row, the current row, matrix rows n. And the do times macro also gives us the possibility to return a value if the iteration has finished. We return the matrix. Also want to iterate over the columns. Yep. And for every row and column, so for every particular element of the matrix, we want to set its value to the value returned by the generator function. So setf. Let me just write this. I'll explain it in a few seconds. Mij, and the value will be fun call of the generator function with the arguments I and j. Okay, short break at this point. I used the function matrix add. Thing is, we and also other users of the linear algebra package will need a way to access elements of the matrix, and we'll just in a few seconds provide a function called matrix add exactly for that reason, which has the argument. The first argument will actually be the pointer to the matrix or the matrix variable, and I and j will specify the ith row and jth column of the matrix. Okay, so that's it for in the case that a generator function was specified, and otherwise we just again set the data slot of the matrix to a newly created array. Again, take the next row. The element type is single float again, and the initial element will be 0.0, and we return m as well. Okay. Right now I cannot. I could, but it wouldn't make sense to compile the function because the compiler, of course, doesn't know about the matrix add symbol, and the function that is associated or will be associated with the matrix add symbol. So we'll write that first. Say dfun, because in this case an ordinary function is enough. Matrix add. The arguments will be, as I said, the matrix, ith row and jth column, and this is nothing more than just returning a reference to a certain position in the matrix data array, and that will be plus times I matrix columns m j. Okay, so the last part is just some basic arithmetic to access the correct position. You might ask yourself why I didn't specify a two-dimensional array instead of a one-dimensional array. Of course, Lisp can deal with arrays of I think at least 7 dimensions or so, but I don't know the exact reason why, but a one-dimensional array, and which is actually called a vector, is faster when accessing it than when you access two or more dimensional arrays. Okay, so this matrix add function only allows us to read elements. We also need a way to set elements, and this is why we need a function called setf matrix add. Setf is a special thing and always expects value as its first variable. It's basically the same as the above function, almost the same. We'll set the indexes in the same matrix as m, j, and we'll set it to the provided value. Okay, that's it so far. A lot of new symbols that we have here. Let's export them. Matrix add and setf matrix add. Because there's an empty space, as you can see at this point in this symbol's name, we need to enclose it in vertical bars. Good, now let's compile it, see what happens. 0 errors, 0 warnings, 0 notes. Very nice. That's it. Good. The next thing that we need is a way to copy a matrix. I just assume that you know the difference between shallow and deep copies of objects. Just go ahead and define the corresponding method, copy matrix, which takes a matrix as its first and only argument. What we'll do, make instance matrix. Rows is the same number of rows, of course. Columns is the same number of columns. And data, this is why we need the keyword data in the first place, is just a copy of the data array of the matrix. Good. Control CC compiles just this particular function. Again, no errors. Don't forget to export it. Copy matrix. Good. Good. Go ahead, and of course we need a way to transpose a matrix. We want to get a transposed copy of the matrix, as we define the function transposed. M again is the only argument, and let's say we have a result. We can even make it easier by using the generator function. We create a new instance of matrix. We have to swap the number of rows and columns. So rows, columns. And now this is the first time we're actually using the generator function by providing the generator keyword and using a lambda function. I and j will be its parameters, standing for again the ith row and jth column. And what we'll do, we'll just return matrix add the jth row and ith columns element of the original matrix. Okay, that's it. Nice, isn't it? Good. So transposed is the next. Compile it. 0 errors, 0 warnings. You may see the style warnings here. We can safely ignore them. They just tell us that we are redefining certain methods and functions. So we can go ahead. And maybe so that we can at least test our previously written functions a little bit, I, by the way, recommend you to write some test cases, test things. I don't want to waste time with this here at this point, but certainly I'll later go and do it for myself. However, let's write a print function, matrix print maybe, okay, and again, yeah, we iterate over the items, do times I matrix rows m. I want to return nil because most of the output functions just return nil at the end. Matrix columns. Format t. Format is a beast of a function or a macro. I don't know exactly. We just want to make sure we have 7. The fields width is 7. We have 2 digits after the point. And 2 spaces in between. Matrix add mij. That's it. Then when every row is finished, we want to terminate print. That's just basically a new line. Okay, that's it so far. Compile it. Perfect. Good. Let's also export this function. Compile the whole thing. And now we switch to the REPL, to Slime's REPL. Or not Slime's REPL actually, but Lisp's REPL. And let's if now we wanted to use symbols exported by the package linalg, we'd always have to precede those symbols with linalg. We don't want to do this right now, so we say use package linalg. T tells us that we're fine. Let's define a global variable m for testing and say make instance matrix, 5 rows, 10 columns maybe, and the generator function lambda ij just returns random values between 0 and 10. Okay, fine. You see m, and now this is a very nice slimy, slime related thing. We can move the mouse over here. Of course you can also do it with the keyboard, but I'll use the mouse instead at this point. Say inspect. Now you see this m actually here is just a symbol, and as Paul Graham once said, there's more to symbols than meets the eye. A funny expression, I think. You can see that the symbol's name is also m, and that it that it's bound to a global variable, and the global variable is an instance of our matrix class. Symbols can also be bound to functions, and they can have properties, but nowadays I think nobody uses this anymore. However, it exists. Good. Let's go. Let's descend a bit and have a look at the matrix. And there we see, that's very nice. We have 10 columns, we have 5 rows, and we have a one-dimensional array with random values. Q to return to the REPL, and let's print the matrix and see what we have. Ah, it looks nice, doesn't it? Now we can try what happens once we copy the matrix. Actually, the output should be the same, yeah, but this is definitely another object. You can see, by the way, Lisp prints it, matrix, and this is something I think like a pointery thing. So if we copy it, you can see these are distinct objects. Good. Now we want to make sure that our transpose function also works. Let's print a transposed of this. Okay, 5, 0. Okay, that's nice. That's exactly what we wanted. Everything works up until now, so we can go ahead. Of course, we need arithmetic functions, and why not start out with multiplications? In this case, we'll use a method instead of a function, because there are different ways to multiply matrices. For example, we might want to multiply two matrices, or we might want to multiply a matrix and a real value. So the first one, we'll call it M star, and we'll specialize it. Let's not call it M, but A instead. Two matrices with the names A and B. And this is basically also very, very easy. We would just create an empty... No, first of all, we have to assert that the matrices have the correct dimensions. So we want to know that the number of columns of A equals the number of rows of B. Then we want to create a result matrix. And again, we could use the generator function, or we can use an iterative way, whatever you like. There are so many ways. In this case, let's just do it in a more iterative way. Okay, make instance matrix rows will be the number of rows of the matrix A, whereas the number of columns will be the number of columns of matrix B. And now we would like to iterate over the matrix. As you'll see in a few seconds, we're going to have a lot of duplicate code, and I'll provide you with a solution for that later on, but first let me finish this. Okay, matrix rows results, and we'll return the result in the end. B times J, matrix columns result, and for every element we have to do the third way. This is a very straightforward way to multiply matrices, so please no flames for that. Do times K, matrix becomes A. Basically we just increase matrix at result I J with the product of matrix at A I K with matrix at B K J. Okay, done with that. It's our matrix multiplication. Let's export the corresponding symbol, compile it, see if it works. Again, 0 errors, 0 warnings. As I just promised you, it would be very nice to have a way to iterate over matrices, and this is where macros come in handy. So we'll define our own. Since most of the iterative macros are called something like do whatever, we'll stick with do matrix. Our arguments will be a matrix, and I and j as counter variables, standing for the current row and current column. An optional argument ELT, and of course the body of the macro. Macros look at first a little bit disturbing, but just write 1 or 2 or 3 of them and you will pretty fast get used to them. They're really, really nice. What we'll return here is basically the loops from below, matrix rows result. Sorry, that's completely matrix rows of M, return M in the end, 2 times J, nothing here. And now we have to distinguish, because the cases where ELT has been provided or not. So we see if ELT has been given, then we want to return a simple microlet where we make use of ELT. And ELT will be replaced by matrix data Mij and the body, or else just the body. Okay, may look confusing at first, however, instead of all this crap that we've written here, we'll use our macro in this place, say do matrix, result ij, and yeah, we want to access the element, and our body will be nothing else but the third loop that we had here. Since we have provided ELT, we don't need all this, we can just use ELT. And okay, now Lisp itself provides a way to print and expand macros. Of course, Slime also does it for us. We place the cursor at the parenthesis right before the macro that we want to expand, and hit Ctrl+C, Ctrl+M, and see what it expands to. Very nice. Do matrix expands to something that we don't want because we haven't compiled do matrix yet. Okay, do it now. Compiled without any errors. Now hopefully this works. Okay, you can see that's perfect. It expands to exactly the same loop that we had before. However, now we are able to use do matrix wherever we want to iterate over all the matrix elements. 2 times I matrix rows. Yeah, looks good, all looks good. Good. So now we need a method to multiply matrices and real values. That's something like scaling in this case. And I'm sorry. Our result at first will be a copy of the matrix. So result will be a copy of the matrix M, and then we'll again iterate over it and multiply all elements. Else we could also do something, yeah, maybe this might be a little bit more interesting. Do it this way. We create a new instance of matrix. Just the exact same number of rows, same number of columns. And since we have the data keyword, we can call map on the original array, and this map should return us a vector. Since I said specialized arrays, or one-dimensional arrays, so sorry, are called vectors. And our function in this case will be lambda, which takes only one argument, I, and will multiply I and s. Good, that's the function, and the first and only sequence will be the original array of the provided matrix. Compiled without any errors, and okay, then also need it vice versa, and matrix. And okay, I don't know if the compiler is smart enough to exchange this, but anyhow, to not prolong this, we just call m star with the arguments interchanged. Compile it this way. Good, nice. Since this way we are only able to multiply exactly 2 arguments, we would like, since let's start out differently. Usually Lisp operators like plus can take an arbitrary number of arguments. If you look at the very bottom of the screen, you see that plus has specified a rest here, so we can take an arbitrary number and they will be added together. And we would like to have it for our m star method as well, so we can take whatever arguments and multiply them, as long as, for example, if we talk about matrices, the dimensions fit together. So an ordinary function is enough at this point, call it mult, and we'll also only have a list of operands. And only in case, so the first thing we have to test if this is a non-empty list. So when const operands, we'll use an accumulator, which is just the first element of the list of operands, and iterate over the rest. Do list in this case instead of do times operands, and we'll return the accumulator in the end, and we'll update our on every iteration step. We'll update our accumulator with the result of calling m star accumulator operand. Compile it, 0 errors, 0 warnings. Don't forget to export that symbol as well. So if I remember correctly, we had this matrix object here. Okay, let's see, let's call matrix print once again, and then let's call matrix print, and first we take the basic case, we multiply by 3.0. That's exactly what we wanted to have. You can see 5.1 times 3 is 15.3. Do it the other way around. Again, what we wanted to have. Now, if we want to multiply the matrices, we have to make sure that the dimensions fit together. So we multiply m with its transpose, invalid number of arguments. Why is that? Where do we have 3 arguments? Now, I think this is the first time the debugger has come up, and we can see that actually I can't tell too much from it right now. Let's see what happened here. M star, M transpose M. This is the M star function for the copy of the matrices. This assertion looks good. Okay, what is this? You see, this was underlined, move the cursor over it. The function was called with 4 arguments, but wants exactly 2. So what happens here? We increase ELT, and we increase it, actually with, this seems correct right now. There may be an error in do matrix. So let's once again expand it and look at the result. So what we have here is symbol macrolet ELT matrix data result ij. That's okay. Then do times k matrix comes a. That's also okay. And increase ELT by matrix at aik. Looks good. However, Lisp doesn't like it. Do times f. So yeah, that's actually correct. Maybe let's try this here. Results j. If this works. Okay, this indicates that something is wrong with our symbol macrolet in this place. Symbol macrolet and ELT matrix data mij. Let's once again version and look what do matrix expands to. It says semicolon ELT linkf ELT matrix add. Okay, now I see the reason. It's fairly easy, but was hard to spot anyways. Instead of using the function matrix data, we of course have to use matrix add in this place. Compile it again. Compile m star. It compiles fine. No message here. Try the thing again, and it works as we expected. Good. So now that we have done the multiplication and also exported the corresponding symbol, we might want to add or subtract matrices and start out defining the corresponding functions. Def method, or maybe a simple defun would suffice here. Defun n plus. We want to add an arbitrary number of matrices. So operands, and again operands. First one, our accumulator will be a copy of the first matrix operands, and then we'll iterate over the rest of the operands, do list operands, and return the accumulator in the end. Use the do matrix macro to add, or again we could directly access the data array instead of iterating over the matrices elements. So what we do here is we say we call map into, and the result sequence is matrix data of the accumulator. Our function will be simply plus, and the sequences are matrix data of the accumulator and matrix data of the current operand. So that's it. Okay, let's compile it. Worked right away. Export m plus. Of course, we also define m minus. Just export right away. Again, I could just copy the code and exchange every plus with a minus, but this really longs for the use of another macro, and we'll use a macro that programs for us actually. Call it def macro, def element wise op function, and this function should have a name and use an operator, and we'll return. Let's be we define a function with the given name as the operands. Copy the code from here, and as long as the operands is a non-empty list, the accumulator will be a copy of the first matrix, and then we'll iterate over the rest of the list operands. And okay, so we only have to exchange this plus with comma op, and that's it. However, if we look at this, we could one could think of using the map command or map into maybe also instead only the command instead of iterating over the list. But what we also want to do is we want to make sure that all matrices have the same dimensions. We'll use another macro for that. Insert same dimensions. Its only arguments will be two matrices, and it will expand to assert and equal matrix rows A, matrix rows B, as well as the quality of the matrix columns of A and the matrix columns of B. So if this is not the case, then we output put matrices must have the same dimensions, providing A and B. Good. Compile it. 0 errors. That's what we'll be using here. Assert the same dimensions, the accumulator and the operand. Go at the beginning and expand this macro and see, okay, there is an error while passing arguments, invalid number of elements. Yeah, don't need the parentheses here. Expand it again and see, okay, assert, and that's exactly what we wanted to have. Compile it. Now we can use this macro again to simply define our functions that element-wise of fun. The first one we want to have is plus, and our operator will be, let's do it this way, compile it again, will be plus. We also want to be able to subtract, take this operand. You could also now think of multiplying the element-wise multiplication of two matrices or whatever. You can use whatever operator you like. Okay, that's it. Warnings, undefined variable. So let's see what this expands to. Define m plus, rest operands, when const operands. Let the accumulator be a copy of the first matrix. Then we'll iterate over the rest of the operands. There's a small error here, as there is in this multiplication thing. Also, because we only want to iterate over the rest of the operands in both cases. So see, this is what happens when you don't program exact tests. Okay, use this here. But there must be an error still. So it's a copy of the first, then we iterate over the rest of the operands, assert that they have the same dimensions, and map into, with the correct function, the matrix data, and again matrix data. Okay, so why this gives us an error, I don't know right now. Yeah, I have a he complains about a variable a. And this variable, of course, is... I see. This error is related to the use of the first macro assert same dimensions. And within the backticks, we have to precede the variables with a comma. Sorry. Just insert the commas. Compile it, compile this, and now this compiles very nice. Go to the REPL, and, matrix print m plus and m. Yeah, that's because we didn't we have to compile the whole file again, and there's a conflict because, yeah, the thing is, I just entered m plus and tried to use the function m plus and the Common Lisp user package. That's what you see here. And as soon as I entered that m plus, the symbol m plus was interned by that package. However, our actual m plus implementation resides in the linear algebra package. And if now we export m plus from the linear algebra package, it conflicts with the same symbol in the Common Lisp user package, which we just accidentally interned. And thus we now say that we want to resolve the conflict, type 0. And sorry, here we type 0. Now he switches to here, and we say that we want to use the first one. Okay, so go to the REPL, whatever happened here. Okay, matrix print plus plus. Okay, if you remember, the former matrix was 5.1, 0.08, and if you now have a look at the addition results, they are okay. Okay, 2 times 0.08 is of course not 0.17, but since we are only displaying the first 2 digits after the comma here, this may be due to rounding. Let's proceed with the functions that we still need. We are quite finished with the matrix related part. However, we also have to deal with vectors. Since vectors are only special cases of matrices, we can define macro instead here, say make vector. This is going to be an interesting macro. We have the arguments dimension and maybe the keyword generator, because we want to be able to use another form of generator functions for vectors, also for vectors. And also we want to have a orientation of the vector, which we specify via the 2 keywords row or column. And we'll make the default orientation a column-wise orientation. So at first, we see what the orientation is. And for the case column, we create an instance. So we have to use the backtick here. We create an instance of matrix, which basically has dim number of rows, but only 1 column. And now we have to distinguish if a generator was provided, then we return generator. Okay. Actually, that's not it, but that's almost it. When I said we wanted to use a special version of the generator function, our usual generator function took 2 arguments, since matrices are usually 2-dimensional. But in the vector case, we obviously do not need this argument. So why not create another surrounding closure, as it's called, lambda, and maybe we use the symbol k. And what k will do, will basically call the provided generator function with we have I and j here, and we'll call the generator function, but only provide the row related argument. Good. And I'm using the symbols I and j. I don't want to clutter anything, so I create the generic symbols I and j. At this point, okay, let's move here and indent this a bit. Okay, this is the first case. The row case is very similar. Matrix rows this time is 1, calls is dim. Here we have the same. Okay, and in all other cases we want to signal an error, unknown orientation, and with the orientation. Compile it. See if we have errors. Yes, we have them. The value near is not of type or vector character base string path name stream, whatever that means in this case. Let's see. This is okay. Our gensims are okay. Orientation case macro is okay. Make instance matrix dim. This is okay. Okay, we splice it here. Then generator. Yeah. Function key. Otherwise, this couldn't make any sense during evaluation. Anyways, we have an error. Okay. So this comma is too much. Compile it. Okay, then this should be replaced with a J instead. However, there is still an error. Let's see what he says. Deleting unreachable code. Why should it be unreachable? What is Emacs doing here? This is the first case. The second case. Because there's one pair. This is too much. Now everything's fine. Very nice. So if now, let's try out the macro. If we say make vector, for example 10, this expands to make instance, matrix row is 10 equals 1, that's perfect. Or if we say orientation row, then we have 1 row and 10 columns. Again, the other way around. 10 rows and 1 column, that's nice. And if we also want to specify a generator function, we can do that. We just need one parameter now, say random between 0 and 100. Okay, there's no generator function, that's not what we want. It's not necessary to test if this is a function pointer. Compile it again, expand, and now this works. We have a generator for lambda taking 2 arguments. This is our enclosing closure, and then we have a fun call to this provided function with the row. Yeah, very nice. Okay, let's also export that symbol, like vector. Okay, now there are again 3 convenience functions that we are going to need, namely vector x, vector y, and vector z, to access the first 3 elements of a vector, because mainly we are of course dealing with 3-dimensional vectors. And again, we could use a macro, but this is such a short thing that we can yeah, actually we will be using macros, but not for what I intended at the very beginning. We just say that macro like x for this vector, and we'll return matrix at b 0 0. Okay, backticks. Then another macro for the second coordinate, for the y coordinate, matrix at b 1 0. And third one, last one, z, matrix at b 0 2. Okay, compile it. Again, mistake. Matrix add, of course. Again, forgot the comma. Very nice. Don't forget to export those. Compile the whole file. Okay, everything is still nice, still fine. Okay, there are 3 or 4 functions left on my notepad. The first one being the length of a vector. That's a nice thing because we can use the reduce function. Okay, so first of all, let's call it back length. Analogous to the upper functions, back length of v will be the square root of the sum of the elements, or actually no, not the sums, but instead 2 argument, one argument, we have 2 arguments, we have plus I and j times j. Our initial value will be 0.0. Okay, of course there is an error. It's late in the evening and the variable v is defined but never used. Yeah, that is indeed not so good. At this point we have to insert matrix data v and whoop, our error goes away. The vector length. Let's export it and try it out. Length. Compile it, switch to the REPL. The parameter v make vector 10, and the generator function that we're going to use will k always return 1. Value 1 is not of type single float. Okay, so we take 1.0. Print p and try to determine its length. Okay, 3.16. So the square root of 10.0 is exactly 3.16. So our function is working correctly. Then we need a way to normalize a given vector. At least we prefer a normalized copy of the given vector. So normalized v, and at first let s be the length of the given vector. And now we have to distinguish two cases. If s is not 0, doesn't equal 0, then we return an instance where with the same dimensions sv, sv, and in this case we could use a map again, or we can use a lambda function as a generator. Let's for fun use a lambda function. The lambda function is ij, and okay, every element will be, actually this is not good. We'll use map instead. We'll use map. Our result will be a vector, and our function will be a lambda that takes only one argument and returns the product of I and not the product, but instead we'll divide I by s, and our first and only sequence is matrix data of the provided vector. Okay. That's the case when s doesn't equal 0, and if it does, we just create a new vector or as a copy of v. Okay. That's it. Compile it. Normalized. Export this as well. And see what it does with our with a vector that we just defined before. Check it with the vector length. This should be 1.0 now, and it is. So this normalization function works also well. And the only thing that we really need now, still need, is a function that computes the cross product of two given vectors. Let's say A and B. So what we return is say make instance matrix, and this is only actually we should maybe assert cross product is only meaningful and valid for three-dimensional vectors. So we should make an assertion that the number of matrix rows of A is 3, and an end, okay, that the number of columns of A is 1. So in this case we would make sure that this is a three-dimensional column vector. Same for B. You know what, why not use a macro instead? Assert three-dimensional vector, or no, make a predicate is three-dimensional vector b. So what we return is a we can use a function instead. Once one gets used to the macros, one may tend to use them too much. We'll just use the function is three-dimensional vector instead, and return either or and matrix rows A3. Okay, yeah, now I see another error. Maybe it becomes clear. Matrix, those functions vec(x), vec(y), and vec(z), they assume that the vector is a column vector, and maybe we should, we could distinguish either column and row vectors, or I don't know. We can expand to array of matrix data v and 0 instead. This is perfectly fine since we expect one-dimensional arrays. Copy that line here. In this case 1. In this case 2. Okay. So again, let's deal with our three-dimensional vector predicate. So either this we have matrix rows 3 and columns 1, or, and the name is V of course, or we have matrix rows B1 and matrix columns 3. Okay, we want to be as general as possible, so this is necessary. Now we assert this three-dimensional vector A and is three-dimensional vector B, and we return a three-dimensional column vector in any case. So columns 1, and data will be an array with dimension 3, of course. Element type will be a single float, and the initial elements will be a the following vector. The first one is minus the product of vec y of A and vec z of B minus vec y b vec z A. The second is vec z A, vec x b, vec z b, vec x A. The third one finally is vec xa, vec yb, and vec xb, vec ya. Good. Compile it. Again, an error. Let's see what the error is. Initial elements is not known as argument as keyword. In this case, okay, we can just look at the bottom. Initial contents is the right term, so we use that instead. Compile it and ready to go. Cross. And very basic thing that we could use is let's say we make instance of matrix rows 3 equals 1, and data is a one-dimensional array of vector 0, 1, 1. Invalid number of arguments, and this is very clear because our cross-product function expects 2 arguments, another one, vector 0, 1. The value 0 is not of type float. Okay, where do we have a 0? Yeah, it's also fairly easy to make these floats. print the result 0, 0, 1, and that's it. Okay, I realized this is really a lot that we have done, but this was also really necessary. We need all this linear algebra stuff, and yeah, this is of course not the fastest code, but it allowed me to show you some fancy properties of Lisp and some different ways we could deal with things. Just think of either using lambda functions in terms of using our generator functions, or map, or reduce, or yeah, so many things, and especially the macros. And yeah, I hope you enjoyed the first part of the tutorial. Thank you for listening.